At the end of class on Friday, I'd asked all of my students what math concept they wanted to cover most as we're starting to head towards the AP exam. And the topic that came up the most, that the majority of students wanted to cover, was chi-square testing. So let's talk about that a little bit. In science, what we often want to do is test a hypothesis of some kind to see whether, for example, one variable has an effect on another, like height and weight, or to see whether two groups are different, like whether the colors of M&Ms in one bag are different from the colors of M&Ms in another bag. And what statistics lets us do is it gives us the mathematical tools we need in order to determine whether the two groups are different or whether a variable has an effect on another, or all the different things that we want to do to confirm or reject a hypothesis. Statistics gives us the tools to answer tons of different types of questions that we have in science with different types of data. Depending on the type of data that we have and the experiment that we're running, there's going to be some test that matches both of those factors that's able to help us explain whether there is a relationship between the things that we want to determine whether there's a relationship between. The chi-square test is a really special test. What it lets us do is to detect anomalies. Let's say that I have two bags of M&Ms, and I want to determine whether the color counts in one differ from another. Maybe they're made in two separate factories, and I want to determine whether they calibrate things in the same way to get the same ratios of colors into each bag. What the chi-square test lets us do is to compare these different counts of categories for two different sets and tell whether they are the same or not. This is a pretty powerful idea and can be applied to tons of different situations. If I have some observed data and my hypothesis can give me some kind of expected data, what I want or what I could expect to see if my hypothesis is true, what the chi-square test lets us do is to compare those to see whether I'm right, whether my hypothesis is right and supported, or whether it's rejected because the data is far away from what I expected using my hypothesis. The chi-square test is also powerful for tons of other things. It can let us tell independence, whether two variables are interacting or not, like the role of one die and the role of another. They shouldn't be interacting, and the chi-square test lets us see whether that hypothesis is correct. The chi-square test can also be used to test homogeneity, to see whether something is evenly distributed between a bunch of different groups. To see some of this power, let's take a look at one example for a different type of test, one that we will use and have used in bio, the idea of using standard errors of means to compare different groups. Let's say that I want to determine whether two lakes have differently sized bullfrogs. I go out and I weigh a bunch of bullfrogs. Let's say I weigh about 50 of them. And I want to know whether the two groups have some statistically significant difference in their weights. The mean is some summary statistic. It summarizes all this data on bullfrog weights from Lake A or Lake B into one single average, a number that describes what could I expect if I were to take another bullfrog out and I wanted the best guess at what that bullfrog's weight would be. What number should I choose? That's what the mean does. The standard error of the mean describes how certain I am about that mean. Let's say that I sample just one bullfrog. I don't know how spread out the data is. I have no idea whether the other bullfrogs could weigh up to 1,000 grams or whether they could go down to 2 grams. But as I add more bullfrogs, I can get a better sense of the spread of the data, and I can get a better sense of the mean. Let's say that I use just the first 10 bullfrogs that I collect, and I try to get some sense of the means and use them to compare. If I take my first 10 data points and I use them to create that mean, that summary statistic of them, I get 161.3 grams for Lake A and 113.5 grams for Lake B. It seems like there's a pretty big difference between the two, but how certain can I be about that? What standard errors let us say is that the more frogs that we collect, the more data we have, the more certain we can be about our estimate of the mean. If I were to try and create some guess for the mean using just the weight of the first frog, my best guess is just that weight. If I get one frog and it weighs 137 grams, and I was asked, what's the weight of the average frog in Lake A? I would probably guess 137 grams. But the big idea is that as we collect more data, my estimate for the mean should get closer and closer to the true value of that population mean. When I take the sample, as the sample size gets larger, my error in my estimate gets smaller. The more data I have, the closer I should probably be able to get to the truth as to what the difference is between the sizes of frogs in these two lakes. The way we can tell how good our mean estimates are now, or how variable they could be, is with that standard error of the mean, describing the spread, or the range upon which we think the real mean could fall. The actual data for the frog weights follows some kind of distribution. There's some spread in that data. As we start with very small frogs, we might have very few of them. This is our frequency. This is our weight. As we get closer to the average, that frequency might increase. It might plateau, it might suddenly jump down. Maybe there's another bump here. But there's some distribution that it follows. What the standard deviation captures, in some way, is how spread out the distribution is. It adds all the squared errors of the data, how far away they are from the mean. The closer our data is to the center, the more centered it is, the smaller our standard deviation. The more spread apart it is, the greater our standard deviation. Our standard error of the mean, how good our mean estimate is, depends on that standard deviation. The more spread out our data is, the more likely it is that our estimate for the mean is further away from the true population mean, because it's more spread out. We might be getting really heavy frogs or really light frogs. There's one other factor, though, that we need to consider, and it's that as we get more data, our estimate for the mean should be getting better. And what happens is that it follows this relationship. It goes down with the square root of n, the number of frogs that we sample. If I sample 100 frogs, then the standard error of the mean is 1/10 that of the standard deviation. The more frogs I sample, the lower the error in this mean, the closer I think my mean is to the actual population mean, or the more certain I can be about it. For these particular data sets, for those first 10 samples, the standard deviation for the bullfrog weights in Lake A were about 60.32. Describes that spread of the data. For those in Lake B, it's about 44.95. These are both in grams. As I sampled 10 frogs from each of these to get these means, I take my standard deviations that I got, divide them by the square root of 10, and that gets me my standard errors. In this case, for bullfrog weights, my standard error for Lake A is 19.07 grams. That's how far, I think, in some way, the true mean could be from my estimated mean. It describes in some way that distance. If I do the same calculation for Lake B, I get 14.21 grams. Now, how could we use these standard errors, these descriptions for the spread or our uncertainty in our means, to actually see whether our two groups are different? We can draw two standard errors of the mean up and down from our means. The reason why we draw two is that it covers 95% of possible values. What we can say is that we're 95% confident that our real population mean is somewhere between these two bounds. We can do it for both of them. For Lake A, we're 95% confident that our mean falls between these two bounds. We can be 95% certain that the real population mean falls somewhere between 161.3 minus 2 times our standard error down here to 161.3 plus 2 times our standard error of the mean up here. But we can say the same thing for the bullfrogs in Lake B. We're 95% certain that the real average bullfrog weight, some real parameter that we think is determining these populations, or that we could say is between these two bounds for Lake A and these two for Lake B. Now, looking at these two bounds, what we can say now is that they're overlapping. It's possible within the 95% for this one, within that 95% confidence interval, we could call it, and within the 95% confidence interval for Lake B, our population mean could be within both of those, for both Lake A and Lake B. And so what we'll say is that we can't be so certain. Despite the 50 gram or so difference, we can't be so certain that these two lakes have statistically different sizes of frogs. As we collect more data, it's possible that our real mean that we'll actually converge to will be the same for both lakes, within these 95% confidence intervals for both of these lakes. As we collect more data, though, we could see that we might get more certain about this difference or less certain, and we could say that it actually is between the two. So let's see what happens if we use some more data. Let's say we collected 1,000 frogs. I've come back, I've collected the data from 1,000 frogs for Lake A and 1,000 frogs for Lake B. And what I've seen is that my standard deviation remains somewhere around these two values. That standard deviation that I'm getting, here it's that sample standard deviation from earlier are 10 frogs. And as we collect 1,000 frogs, it'll be some slightly different number, but it should hover around the same ballpark. It's describing that spread of the data, and so whether I collect 10 or 100 or 1,000, it should be somewhere around the same value, just describing what that actual spread is, or getting close to it. But my standard error, the mean, shrinks. As I collect more data, I can be more and more certain of the mean. I've seen more frogs. I know where more frogs lie. And that makes my standard error far smaller. I can be more precise about those ranges where the mean probably is in. And in fact, if I collect 1,000 frogs, it just moves that decimal point over for each one. If you'd like, you can take a look at this formula and see why that's true. When we go from 10 bullfrogs to 1,000 bullfrogs for each one, why, if the standard deviations stay the same, which they won't actually, but they'll be around the same ballpark, why that decimal point just moves over one. For practical reasons, though, for all practical reasons, what that really just does is make our estimates far more certain. If, let's say, our means hovered around the same points, which, as before, which they don't have to, our error bars are 95% confidence intervals from 2 times our standard errors up and down now don't overlap. We can pretty confidently say now, in fact, very confidently say, that the bullfrogs in Lake A are larger than the bullfrogs in Lake B. What standard error of the mean has let us do is take a bunch of data, find the mean, and describe how confident we can be in what range we can be that confident that the real mean, that the real population mean falls somewhere there. Now, what if our data isn't continuous like this? What if we don't have a set of weights, like here, and instead have something like a set of colors, like in the parking lot car lab? How can we tell whether two groups are different then? There's no standard deviation that we can calculate there if we're talking about reds and greens and blues. We can't add words or add colors. But we know there's got to be some difference between them, or some way to tell. We're counting them. There's going to be some statistical measure we can use. And that's what chi-square testing lets us do. So let's see what that looks like. What chi-square testing allows us to do is it allows us to measure anomalies and to check how surprising that anomaly is. Before we even get into how it does that, there's one important idea to especially chi-square, but to all the statistics that we've got to cover first. And that's the idea of degrees of freedom. Degrees of freedom represent how many different things we can change in our data. Now, what does that mean? Let's say that I want to know whether playing first in Connect 4 gives an advantage to the player who plays first. And I watch 100 Connect 4 games. From those 100 games, I see that 60 of those games led to the person who played first winning. If there are no draws, how many games were won by the person who played second? You can probably guess 40. In my data set that I'm going to use for chi-square testing or for any other purpose, whether I'm visualizing with a pie chart or anything like that, I'm showing these two numbers. 60 games were won by player 1, and 40 were won by player 2. Let's say that I were to change one of these numbers, though. And I keep the number of games played the same. If I change the number of games won by player 1, the number of games won by player 2 has to change with it. There's only really one way that I can change these two numbers. By making this number go up or down, I make this number go down or up, and vice versa. There's only really one parameter that is flexible. That's what a degree of freedom is. It's one place where we can wiggle things, where we can change things, and keep our data making sense. Let's say that I want to describe where a point is located on a Cartesian plane. What information do I need to describe that location? An x position and a y position. And that's it. I don't need any other distance. I don't need to know how far it is from the center or anything like that. I just need one point of data, another point of data. There are two values I can change, the x position and the y position, and get a different point. But if I know those two, I've got my point locked in. There are 2 degrees of freedom there. A really cool thing as well is that even if I were to try and find that point in a different way, with, for example, that distance and some angle, I still only need these 2 numbers. There's still only 2 degrees of freedom, no matter which way I cut it. Only 2 different parameters I can change, and after I change those 2, my point is locked in. As long as these 2 parameters aren't related to each other, only 2 numbers I can change, only 2 degrees of freedom. Only 1 number I can really change, only 1 degree of freedom. Now, why do we care about degrees of freedom at all when we're talking about statistics? Let's say that I have some set of data with some number of degrees of freedom. Those degrees of freedom describe how many ways that data can wiggle, how many ways that data can be moved around and still make sense in some way. Those numbers of degrees of freedom also represent the ways that that data can be anomalous. The more ways it can be anomalous, the more likely it is that it's going to look anomalous just by chance. And we have to account for that. The more degrees of freedom that we have, the higher our threshold should be for what we consider a surprising amount of anomaly. If I was to talk about wins and losses with this Connect 4 example, there are only 2 things that can happen. Player 1 can win or player 2 can win. Only 1 degree of freedom in total. But let's say that I were to include all sorts of ways. Every single way a game of Connect 4 could ever be won. Now there are tons of degrees of freedom, tons of numbers that could be changed and altered along with each other. And I might, just by chance, see that 2 of the games looked the exact same. That's anomalous. Games of Connect 4 are often pretty unique, but it shouldn't be surprising. I looked at 100 games. It's likely that at least 2 of them are going to overlap in some way. What degrees of freedom let us do is let us describe the distribution and describe that threshold for surprise we want to choose in order to detect real anomalies that we think aren't just based on that random chance, but are based on some actual trend or some actual difference between the categories of data. When we take a set of data, we can calculate something from it called the chi-squared statistic. What the chi-squared statistic measures is that amount of anomaly. Based on how far our data is from what we expect, taking all those errors, combining them in some way, we get a measure of anomaly. What we can say is that if there isn't actually any real anomaly, then we'll still get some kind of measured anomaly. Our data won't exactly match what we expect, pretty much no matter what. If I flip a coin 10 times, it won't land heads up 5 times, tails up 5 times for certain. It'll be distributed in some way. There will likely be some anomaly. What the chi-squared distribution does is it describes how that anomaly relates to the number of degrees of freedom. Starting with 1 degree of freedom, our anomaly is probably going to be pretty small. But as we increase degrees of freedom, the spread of these anomalies and the size of these anomalies is likely to get bigger, even if there isn't any true anomaly between our data and what we expect. What we're doing when we calculate that chi-squared statistic is that we get that total measure of anomaly that we then compare with one of the reference tables, like on that formula sheet, which describes for some number of degrees of freedom how likely we are to see certain values of anomaly. And what we say is that we want to be with some level of certainty sure that the anomaly we're seeing isn't just from this random anomaly, but is from some actual difference between our data and what we expect, or not. That's what we're doing when we're testing it. We calculate that chi-squared statistic, which we compare with the set of anomalies that would be random anomalies based on our degrees of freedom. And we see whether our anomaly is surprising, whether we see more anomaly than what we'd be comfortable with saying, yeah, that's probably just from randomness. Now, where will we set these cutoffs for what's surprising based on these degrees of freedom and based on our statistic? What we can do is say that these distributions, these chi-square distributions at different degrees of freedom, describe the likelihood that we'll see certain statistics if our anomalies are random. What we do is we assign what we call an alpha value, or some p-value. It's some cutoff where we say that if our anomaly fits into where, if it was random, there would only be less than a 5% chance of seeing that anomaly, we'll say it's statistically significant. Looking at our distribution for 1 degree of freedom, our chi-square statistic, that cutoff statistic, is at around 3.8 or so. What that means is that if our data did not have some actual difference, no underlying difference between it and what we expect, then 5% of the time, we'll see our anomaly be over that threshold. What we say is that if our chi-square statistic is above that threshold, it fits into this area that represents 5% of our distribution, there's a less than 5% chance that our anomaly would be coming from chance. That's the cutoff that we're using to determine whether our anomaly is surprising. And we can describe it for 3 degrees of freedom, 5 degrees of freedom, for any degree of freedom. For the 3 degrees of freedom graph, if we continue it out, it's somewhere around 7. So this area for the rest of this tail represents the area of 5% of the total area of this graph. And so if our anomaly is more than this cutoff threshold, we can say there's a less than 5% chance that that anomaly would come from just the randomness of the data. We're pretty confident that it came from some actual underlying difference between our observed data and our expected data, which we can use to confirm some kind of alternative hypothesis. That's what we're doing when we calculate that statistic and we compare with that threshold. We're trying to see, is this surprising enough? Does it meet that 5% threshold that we're using to cut off and say, yeah, this is surprising. We're pretty confident that this didn't come from randomness. Just to finish our examples, with that third curve, if we calculate an anomaly greater than that threshold of, for 5 degrees of freedom, somewhere around 11, all the way over here, then we can say there's a less than 5% chance that that anomaly came from randomness, the inherent randomness of the data. If our anomaly's less than that threshold, we can't say that. And so we can't use that to really confirm or support that alternative hypothesis as strongly. It's important that we set some kind of threshold beforehand. So having something that's widely accepted, that 5%, that alpha of 0.05, that p-value of 0.05 is really useful. That way we can't just take our data and say, oh, this looks kind of surprising. Let's say it's surprising. We've got some threshold that we've agreed upon. If it's beyond that threshold, we're going to say that's surprising. Now, how can we actually calculate that chi-square statistic? How can we actually find that measure of anomaly that we can compare against these reference values? Let's see how we do that. Let's take an example to see how we can put chi-squared testing to work. A farmer has 2 heterozygous smooth pea plants and crosses them, producing a total of 10,000 offspring. The farmer has these 10,000 offspring spread throughout a field, but a problem arises. The farmer finds that the bunny has been found eating the crops. The farmer wants to know whether the bunny prefers a certain pea shape. The farmer knows that the bunny prefers smooth peas. The farmer can plant more wrinkled peas, hopefully deterring the bunny. Is there a significant difference in the pea preferences of the bunny? Now, the farmer has kept very close eye on his pea plants and knows that 142 smooth pea plants were eaten and 58 wrinkled plants were eaten. The farmer wants to know, is there some preference that the bunny has? Now, just on first glance, it looks like the bunny prefers smooth ones, but we need to actually compare this with some expected values. The biggest thing for that is we need to look at our null hypothesis. The bunny doesn't prefer any type of pea plant. The proportion of pea plants eaten will match the proportion of pea plants available. If we cross our 2 heterozygous pea plants, we find that 3/4 of our pea plants are smooth. Only 1/4 are wrinkled. So out of the total of 200 plants that the bunny's eaten, what we would say is that we would have expected that out of that total of 200, instead of observing 142 smooth being eaten and 58 wrinkled being eaten, we would have expected 3/4 of 200, or 150 smooth pea plants to have been eaten, and 50 wrinkled ones to be eaten. Now, it already looks like now the bunny prefers wrinkled plants. But how do we know that that's a statistically significant difference? That's what chi-squared testing tells us. Let's just compare these categorical variables and the numbers that fit into those categories. The first thing we do is we calculate the errors in each one. How far away our observed value was from the expected value. These are just some raw errors, these raw differences. We see that there are 8 fewer smooth pea plants eaten and 8 more wrinkled pea plants eaten. As a little side, one thing that you can see is that these 2 are related. There's only 1 degree of freedom here. We have 2 categories, so 1 degree of freedom. Only one number seems to be able to change 1 degree of freedom. And in overall calculations that in chi-squared, our degrees of freedom is equal to the number of categories minus 1. If I tell you all the other numbers, and you also know the total, you can find that last remaining 1. So if I have 2 categories, I've got 1 degree of freedom. Now, back to our calculations. We've got our errors, and one other important thing is that it's not just the size of the error, but as we get further away, our error becomes more and more surprising. The bigger our error, the bigger its impact. An error of 1 and an error of 2 here and an error of 3 here shouldn't be that huge. But the difference between an error of 8 and an error of 9 might actually be pretty big. As we increase our error, it gets more and more surprising. So we square it. Another effect of this squaring is that it doesn't matter whether our error is low or higher, whether it's negative or positive. But looking at our squared errors, that we also then normalize in some way. We center them, or we base them around that expected value. We don't want it to just depend on having huge numbers. That ruins the value of the test. Just having huge numbers or huge numbers that fit into categories shouldn't matter as much. Because what we really care about is how these numbers compare. And so what we do at the end is we divide it by the expected value. We square the error and divide it by the expected value. for each category to get some measure of surprise. A difference of 8 here between 142 and 150 shouldn't be as surprising as the difference between 58 and 50. The percentage difference here is bigger than this one. And so our chi-squared statistic that we're developing from adding the squared errors divided by the expected for smooth and wrinkled, it'll be bigger for the wrinkled than for the smooth because we see a bigger kind of percent difference between them. Now, we can take these values for the smooth and the wrinkled plants, we can add these anomalies up to get our total chi-squared statistic. So if we add these two numbers up, we get 1.707 is our total chi-squared statistic. Now what we have to do is compare this with our reference value from our table. We saw 1 degree of freedom. We decided ahead of time, just in general, that all the p-values that we're looking at are 0.05. We want there to be a less than 5% chance that if we see a significant difference, that it actually was just from randomness. In looking at 1 degree of freedom at p of 0.05, we get some threshold value of 3.84. If our anomaly is bigger than that, our anomaly is significant, we would call it. If it's less than, we won't say it's significant. And what we see is that it's less than it. We don't see a significant difference, even though we do have quite a big difference in terms of percentages. This probably just came from chance, is what we can say. In fact, these values don't exactly mirror kind of, it's more than 50%, it's less than 50%. They're based on that p-value. We're not saying that it is more likely that it is this or less likely that it is this. We're saying that we will not say that there is a statistically significant difference between what we observed and what we expected at this p-value. We won't say that the bunny has some preference. We will not confirm that alternative hypothesis. We don't have the data to support the idea that the bunny has a preference for one type of p over another type of p. Let's look at another example. Let's look at an example of using chi-square testing for Hardy-Weinberg equilibrium. So a population with 100 individuals has 60 individuals who are little a, 41 who are big A, and 43 who are big A. And our job is to determine whether it is at Hardy-Weinberg equilibrium. So let's start by talking about kind of how we would calculate that Hardy-Weinberg equilibrium, just as a bit of a refresher. At Hardy-Weinberg equilibrium, we say that our alleles are independently randomly sorted, that there's no evolution going on. And so, the chance of an individual being big A is equal to the allele frequency of big A times itself, because they need to get 2 big A's. So we take P, that allele frequency for big A, and we square it. And that'll give us that chance. We can do a similar calculation to get our probabilities of seeing big A or little a, and that's how we can calculate some expected values. Before we can get to that, we need to calculate those percentages of each allele. So let's do that. Our first step, starting off with these numbers, we see 16 individuals are little a. 41 are big A, and 43 are big A. From these, we can count that we've got 16 times 2, we've got 32 little a's from here, plus 41 little a's from here. That gives us a total of 73 little a's. For big A's, we can say that we've got 41 big A's from our heterozygotes, 2 times 43 big A's from our homozygous dominant individuals, and that gives us some total of 127 big A's. Using these two, we have a total of then 200 alleles in our entire gene pool. So dividing these two by 200, we get that our P, our allele frequency for big A, is 63.5%, or 0.635, and Q, is 73 divided by 200. It's the percent of our total alleles, kind of imagining all of our genes divided up, our total alleles at R little a. And so that's going to be 0.365. With these two values, we can now calculate our expected number of individuals who are homozygous dominant, heterozygous, and homozygous recessive by taking our P and Q values and multiplying them and combining them. So let's see what they would be. We take our P squared, we get 0.403. And I'm also going to go ahead and multiply it by 100 to get our actual expected number of individuals with that genotype. So about 40. 0.3. For our heterozygous squares, we've got about 23.2. And for our homozygous recessive individuals, we've got about 13.3. These are expected counts. Based on the allele frequencies of our little a's and our big A's, we found that we would expect these numbers. Now, using them, let's go ahead and see what our chi-squared statistic is. We know that our chi-squared statistic is the sum over all of our observations of our squared errors divided by our expected values to normalize it. So let's calculate it for all of these. For our first part, our homozygous dominant individuals, we observed 43 of them. We expected 40.3. We square that error from what we would expect, kind of our deviation from it. We divide it by our expected value, and that gives us our first value. We do it again with our heterozygotes. In total, we would have expected 46.4 heterozygous individuals. That decimal's okay. It makes it more accurate to what Hardy-Weinberg equilibrium would predict. Even though it's not quite an actual whole number amount, it's good. In fact, it's more accurate than what it would be if we would round it. So we observed 41 of them. We expected 46.4 of them. We square that error, and we divide it by the expected value. Gives us our next part of our anomaly. And our last part that will add into our total anomaly, we observed 16, we expected 13.3, we square that error, divide it by the expected. We'll combine all three of these anomalies to get our total anomaly, our chi-square statistic. Before we get to these, I'd like to talk a little bit about the degrees of freedom for a Hardy-Weinberg problem. If you're given these three frequencies, technically, for Hardy-Weinberg, we only really have about 1 degree of freedom. We can even mathematically have things that are more than 1 degree of freedom, but less than 2 decimal numbers. That's technically the case, but we'll treat it as it rounds to 1, as 1 degree of freedom. If we were to move one of these numbers around, the others would have to move suit to keep things actually matching Hardy-Weinberg equilibrium. If we know P, we know Q is another way to think of it. There's only one number we can really change for Hardy-Weinberg equilibrium. For the rest of our Punnett squares and the rest of our chi-square examples, it'll still be our n-1, but for Hardy-Weinberg, there's really only 1 degree of freedom. So, going back to our chi-square calculations. For the first anomaly, we get about 0.181. The second, we get about 0.628. And for the last, we get about 0.548. Now, adding all three of these together, we get a total chi-square of 1.357. And now our question is this bigger than our threshold value? Our threshold for 1 degree of freedom is 3.84. Our chi-squared statistic is smaller than that, which means our total anomaly is less than this threshold. We won't say that there's a significant deviation from Hardy-Weinberg equilibrium, we'll say that we've confirmed the null hypothesis, that there's no difference, and that we are at Hardy-Weinberg equilibrium. One important thing to note is that chi-squared testing, and everything that we're seeing here, deals with counts, not percentages, not things grouped in tens or thousands. It deals with counts of each category. That's important. If we look at that formula for the chi-square statistic, if we were to double all of our values, that part at the top grows faster than the part at the bottom. If we keep our relative proportions the same, if we see 10% more observed than expected, if we observe 110 versus 100, that difference is pretty big. But if we observe 11,000 versus 10,000, that difference is even bigger. And that anomaly, because we're looking at a squared error, grows even faster. That matters a lot. And the reason why is that as we collect more data, we want to be able to say that we are more confident. If our anomaly, our relative anomaly, our percent error is remaining the same, then our data is likely pretty different. It's just like how when we have more data, our standard error of the means got smaller and smaller, as we could more confidently say that we are closer to our population mean. As we collect more data, if our percent differences remain the same, we can be more and more confident that those percent differences are real differences. And so it's important that you're working with counts. If you're given percentages, convert them to counts for chi-square. If you want to do a chi-square using percentages, then you need to multiply your statistic by your total number of observations. So in this case, 100 individuals. But in general, I would recommend working with your counts, observed and expected. But if you want to work with percentages or some probabilities, multiply your statistic that you get using those by the total number of individuals. Thank you all so much for watching, and I hope that you enjoyed learning a little bit more about chi-squared, the test, and how it's used.